Okay, so we're taking a look at quantitative reasoning with harmonic motion, and we have a 2 kilogram cart attached to a horizontal spring vibrating back and forth on a low friction track. So similar to what we've seen before, where the spring is attached and this cart is moving back and forth from some equilibrium position. And we get to decide, a lot of things here. There's a lot of pieces that we know, and it helps when we're given a position-time equation. Okay, so let's first start off and say, well, this is the mass of the cart. That may come into play later. This is the amplitude of the cart. So how far it's going to move beyond its equilibrium position is amplitude. Its maximum displacement either way. This number down here we know is the period. And we know based on our general equation associated with our simple harmonic motion, and we related this to circular motion when we went through and did it, and we got something that looked like that. So when we rearrange and we just look, we can say, oh, 2 pi over t, that's our period. That's how long it's going to take to go back and forth, and t is the amount of time that we're actually looking at. So that's where we are, just starting off, even before we get to what the questions are asking. Alrighty, so let's look. First part. The positive direction is on the x-axis is to the right. Determine the cart's position at t equals 0, quarter time, half time, and 3/4 time. Okay, and as we go through this, we know that the object is going to it's going to move one way, then the other, then back. And the amount of time it takes to do that is the period. So if we can figure out where it starts, we can figure out what it looks like from there. Well, a sine curve, if we were to graph this, a sine curve, okay, with our time being 0, sine of 0 is 0. So our sine curve, this is a positive sine curve, is going to look like this. That would be 1 period. And the amplitude of this is 0.2 and negative 0.2. So we can answer questions based on that just by looking at our graph without even using our equation. So at 0, our position is 0. At a quarter period, so it's right here, our position is 0.2 meters. We're at our maximum amplitude. At half a period, again, we're back at 0. At 3/4 of a period, we're at negative 0.2. And at 1 period, again, we're back at 0. So we could plug that into our equation and solve from there to get our answer. And what you'll find is you'll get sine of 2 pi equals 1 or negative 1, and then we're determining our amplitude or our position based essentially on that amplitude. Okay. Question B, determine the period and amplitude of the motion. Well, the period we already picked out of the equation was 2 seconds. We also picked the amplitude out of the equation as 0.2 meters. Calculate the spring constant of the spring. Well, in order to calculate the spring constant of the spring, there's some information I need to know within this situation. First off, I need to remember back to what I had learned previously that showed us that the relationship that exists with t is 2 pi times the square root of m over k. Now this came from our first investigation when we were looking at the relationship between the maximum spring force and our angular velocity, or our angular acceleration, my apologies. And that was relating our spring force kx with our acceleration and plugging in our equations to match. And what we found was that we got omega was equal to the square root of k over m. Well, if I know that omega equals 2 pi over t, then t equals 2 pi over omega, and then I multiply by the inverse of that to get my equation here. Now, with that being said then, I can solve this for k. And what I'll do is I'll square both sides. So I'm actually going to change colors here to make this a little easier to go through. I'll square both sides. So t squared equals 4 pi squared times m over k. I can divide by all, I'm going to actually multiply k over and divide. So I'm going to bring this over here. So k equals 4 pi squared m over t squared. And these are all numbers that I know. M is 2, remember, and t is also 2. So when I go through and I do this, I get k equals 19.6 newtons per meter. And that's me going through and plugging in the numbers I know, where the mass is 2 and the period is also 2. So pi squared times 2 is essentially what we get. Okay. Next question. Calculate the maximum spring potential or elastic potential energy of the mass spring system. Well, this, remember, is going to be 1/2 kx squared, or where my maximum is going to occur at my amplitude. So 1/2 times 19.6 newtons per meter times 0.2 meters squared. Oops, this is more like 19.7, I see now. 19.7. So then let's do 1/2 times 19.7 times 0.2 squared. And we get our spring potential energy to be 0.394 joules. So that is the maximum elastic potential energy that I have in my system, which means that's the total amount of energy I have in my system. And at some point, since those are my total energy, the maximum of speed occurs when my spring potential energy is 0 and my kinetic energy is maximum, or 0.394. So then I can figure out what this maximum speed is by going through and solving. So my maximum speed is going to be the square root of 2 times 0.394 joules over 2 kilograms. Or, let's see, the square root of 2 times 0.394 divided by 2. 0.627 meters per second. Excellent. Okay, so then our last part is to draw a free body diagram of the cart at various times. Well, then in this case, we need to think about what's going on with our cart. So we said that at the beginning of our situation, we are at equilibrium because we start at a position of 0. So we are at equilibrium. So if that is the case, if I'm at equilibrium, then I have no spring force acting on my cart. So I have a normal force and I have a weight force. At a period or a quarter period, I am stretched maximum positively. So if I'm stretched maximum positively, that means that I'm as far out this way as I can be, which means my spring force is in the opposite direction. So I have a spring force this way, and I'll still have my weight force and my normal force as well. When I hit t over 2, again, I'm back at equilibrium. So I have my weight force and I have my normal force. When I hit 3t over 4, I'm here. I'm at my maximum amplitude inside, which means my spring is going to be pushing outward. So I get a force diagram that looks like this. And then finally, after one complete period, I'm back at equilibrium. So my free body diagram looks like this. I hope that explanation helps. going through looking at equations, breaking them down into its pieces, and then using what we know about spring potential energy, Hooke's law, free body diagrams, and motion equations just to solve.